Anyways, so good. So here we are for the second lecture. So we have had a little bit of a gap, right? So it's good to review. So for today, my agenda is I will quickly review what was in lecture one, and then which was the formulation of the problem, right? We formulated what we are interested in solving. And today we will do the planning problem, which is to say, if we have all the data, somebody has nicely provided us with all the information, granted that we have all the knowledge, can we solve the problem? And it turns out that mathematically, it is a rather simple process to understand how to solve this problem. Okay? But this is under a very, very special assumption, which is that we are given all the data, right? Which is not practically true. So today, what we'll show will work for small problems where we can essentially get all the data, right? Or somewhat medium problems, but this cannot work in general. But the concepts that we develop will be the same. This will be how everything else will also process. So it gives us a conceptual understanding as well. Okay, so we'll review first. Okay, so remember, how did we formulate mathematically our problems? We want to learn to sequentially make decisions to optimize sequential decision problem, and we model it as an MDP, right? As a Markov decision process. And what does an MDP entail? It corresponds to having an environment, which we model as the states of the environment, snapshots of the world, right? Then it has to have an agent, which we model as the possible actions that can be taken, right? And then we need few other things. We need to know how things will move around. If I make a move in the game, or if I place something, or if I drive my car from left to right, the state of the world will change according to some sort of Markov probability, so the transition probability, which we will, depending on an action, will also have that. And when we move from one state, take an action, get to another state, we will know how good or bad our world has been. So we'll get some reward. So this is, and of course, we will factor out the reward in future. So this is our setup, just to recall. Everybody remembers that? Happy with that? Okay. And then the question is, what's the solution? What do we need to do? We need to find a policy, right? Well, a policy one can always find. We need to find an optimal policy. But just to remember, what is a policy? A policy is an assignment of an action when you are in a given state. So if you are in a state, you decide whether you want to go left, you want to go right, whether you want to go up, you want to go down, which direction you want to drive, what move you want to play. That policy is a choice of an action given a state, right? So it's mapped from state space to action. But sometimes we will see, not probably in this lecture, we will not need that. We will be happy mostly with deterministic policies this lecture. But from next lecture, we'll certainly need stochastic policies that don't tell you what action to take in a state, but say, take this action with some probability and take that action with some other probability. So this helps you explore more things, right? Otherwise, you're rigid. You're rigid to doing one thing. Whereas if you have a probability of sometimes trying to do this and sometimes trying to do that, that gives you some flexibility. And what else did we learn? So most importantly, we learned that there always exists a optimal policy. So we are guaranteed by by a rather simple mechanism that there will be an optimal policy. So we saw all of this last time. And the reason why that worked is we can define for every policy a value function. So I've written down the formula for it, which we did last time. But the value function is how much reward you get now, plus how much reward you get in the next state, discounted by gamma, plus how much reward you get in the state after, again discounted by gamma. And you add all of that, that is the value of your current state. So starting from this state, since we have a Markov hypothesis, we can say what is going to be our total sum of all the rewards following our policy. Okay, that's the value function. And we saw last time it satisfies this rather nice equation, which is called the Bellman equation, right? So the thing is that every policy has this equation, which is sort of an affine equation, which we can solve if we want to directly in some ways. But the other thing is that the optimal policy satisfies this optimal value function. So if you have an optimal policy, it will have this value function, which will be max over all of them. And sometimes you can write this equation for it, which we saw last time. So this is just a sort of recap of last time. So were there any questions about last time? Okay, so what are we going to do this time is we're going to say, well, how can we solve this problem? Right? So what do people do when we want to solve a problem? So before I go to the next slide, or I might just even hide this thing for a second. For now, this is too dark. Okay. So how would you like to solve this problem? Because we are, at least in principle, in a math class, not just a data science class, we are thinking about solving the problem, not just implementing the solutions. Right? So how would you start thinking about finding the optimal policy? What can you do? So a policy is a map from the states to action. Can you pick one at random? Of course, you can pick one at random, right? You can pick an arbitrary policy to start with. Okay, so pick one at random. Is this going to be your best shot? Probably not. How do we know? What is something that tells us where is the information about how good our policy is? The value function, right? So we need to really figure out what this thing is for every state S. Now, of course, you could say you could use that formula. What will be a nice way to find the value function? That is the next step. So the first thing we need to know, this is the first part of the problem, evaluate the value function. Second thing you need to do is, can you improve this value function? Can you find a policy that does better? So this is one. Two is, can you find a policy by time that does better? Right? So there is a certain mechanism of doing it. So if you do a certain way of doing it, you will always get something bigger or equal to. And if you get equal to, you're supposed to stop. So this is the basic. I have to turn this thing on to show you that. Okay, just one second. I see. So this is the basic procedure. This is what we will follow. So each of these steps, the mathematics of these steps is what we are going to discuss today. So we start with an arbitrary policy. We evaluate its value function. Then we try to improve use the value function to get a new policy. And you say, is this new policy better If it's better, then go up, evaluate its value function, because now you call pi prime equal to pi. So basically you're saying evaluate the value function for the new policy. For it, now improve that one. Is it going to be better? Whenever you say it cannot be made better, you just output that policy. So the question is this obvious that what your output will be optimal if I do something like that? It gets hung in the middle, right? In some local stage. But as we'll see, we'll have algorithms for all these steps which will do the best thing. So first thing is how to find the value function. Okay. That is okay. All right. So this is no, maybe I shouldn't show you this slide first, but I suppose you read it now. That's a little bit because the whole point is to think, right? I'm not here to. You can look this up on the internet and various books, videos. I am here to make you think. That's my job, right? So the thing is, you're given pi. This is given. How to find v pi? So what is this thing? This is a function from S to A, right? So as a mathematician, or even as those who are here, not mathematicians, but you want to think, I want to find some function, so what should I look at? The first thing mathematics tells us is to look at the space of all the functions. So basically you start with a space of all functions. Sorry, the value function, I'm sorry. The value function is a function to how much money you get, or how much reward you get. It's a number. Pi is a map, sorry, what I should have written. Pi is a map from S to A. The value function actually just gives you the value, how much reward you obtain. So, sorry about that. So we have a space of all such maps. What kind of space is this? It's a vector space. In fact, since it's a vector space, you can say which is better and which is worse by putting a metric on it. So you put the most obvious metric on it, which is max of S belongs to S. Okay, so this is some sort of a norm. This is the metric on this space. And now what do you know about, what will we know about we saw an equation for it, right? We saw an equation that v pi equals, what was its equation again? S is the reward you take by taking the action corresponding to S plus gamma times the probability of going to some other state S prime given the action times the value at S prime. You remember this? So in a matrix notation, we can write this as V pi is R A plus gamma P V pi. And what does that hint? What does that suggest? What does that suggest? That suggests that we can construct an operator here. We call this thing T pi of T pi. So we can always construct an operator like that, right? And then V pi is something that is, what do we call anything that satisfies an equation like that? A fixed point, right? So this is a very often used phenomena in this kind of world. So it's good to think in this way. So all I want you to start thinking in this way. So when you see such an equation, a fixed point kind of equation, you should think of defining the space of all maps. And on that space, you define an operator. I suppose I'm on the right. Where is my?
Yes.
Where is my? Okay, my gun. All right. So this is what we need. So we have an operator, and we have a space, and we want to find its fixed point. What will guarantee that we have a fixed point? What kind of mathematical phenomena will guarantee? If T is a contraction, then it will guarantee that it's a fixed point. So just, I think that's in the next slide. So this is a proof that T is in fact a contraction, and it's pretty much straightforward. So I don't even want to explain it. But you can look at it. It's written out there. T is indeed a contraction. Okay. Why is it? There is only one non-trivial step, the last one. Why can I say the last step? What do I know about P? P is a is a transition probability matrix. So how big is its norm? Less than equal to 1. Right. So this is the only thing that I have not written there. The getting rid of the P holds because the norm of P is less than 1. Okay. So now that we know T is a contraction, we can solve this problem. Since T is a contraction mapping, and whenever you have a contraction mapping, in any modeling situation, not just this modeling situation, in any modeling situation, if you have a contraction mapping, you basically can always do the same thing. You know there is a unique fixed point. You can start with an arbitrary element of your vector space and keep applying your operator iteratively over and over and over again. And it will converge to your solution, to your fixed point. Good. And the rate of convergence is actually gamma, which I did not, I think, write on this mode. So the gamma is the contraction factor here. In the proof of contraction, gamma is a contraction factor, and the rate of convergence is pretty much determined by gamma. Okay, so this is a good convergence always. So let me just say what policy evaluation is. This is the algorithm, if you like. If you look at most, say, data science texts, they will give you this algorithm first, and they'll say, "Oh, it happens, it works out." But we do the other way around, right? It works out. Obviously, it does because of contraction mapping theorem. We don't have to even think why this works. It works. You start with this arbitrary element of your value space. Keep applying the Bellman operator to that, and what you converge to is the value. So this is how this is the first thing you wanted. So we said we want to find the value function. So we have done that step in a very easy, peasy way. But this is something that will recur throughout our course. So it's best to remember something like that. Any questions? All right. So now what do we do next? Our next task is to, now that we have value for pi, we want to know if we can do improvement. Can we make it better? So this is, there are two ways of looking at this world, and this is sometimes the more tedious way, so to speak, but it is more interesting. So what is the improvement? How do we get the improvement? So I don't know if you remember what the function q was. The value function was what one called the state value function, and we also had last time a state action value function. And how did we define the state action value function? Maybe it's time I recall it. 1 second, then I will have to make this dark and recall what the state action value function was. So we are given a policy. Right? The policy, let's just keep deterministic for this lecture. So we have a policy that is given to us, and we are in a state as, and we choose an action A. So Q pi SA is basically you start with as, you take the action A, okay, you end up, well, somewhere as prime, right? Or basically some distributionally, but let's just say as prime. And now from here on, you follow the policy part. Every step on, you follow part. Okay? So now you say, I get a reward first because of A, and then I get the reward according to pi. This is what what we want to call Q pi SA is the total value we'll get by first doing the action A in state as, and only for one step, and then following your policy. Okay, so if you think about it, in the first step you'll get the reward, and then you'll get gamma, p, and the value of pi. Right? So if you think about it, after we go to the second step, you have to apply a discount factor. And each of this will be weighted by your probability, right? And this is what Q pi is. Oh, did I go through it? Oh, yeah. Sorry. Sometimes these things will happen. So this is a recall. And why do I want to recall it? Is in improving the policy, in pretty much in every such situation, you kind of think of this process. So if I want to say, if I know V pi, suppose I only know V pi, so I know V pi, how can I think about improving the policy? What's a greedy way of improving the policy? Really greedy way. Sorry, what?
Trying to try every way possible, try every action way possible, and see which is better.
Exactly. So just considering that I start with the state as, I can take all possible actions, so A1, A2, whatever AN. For each of these actions, I will end up somewhere, and then I will follow my policy, right? So I can consider the Q pi as AI, and I can think what action is best. So what my policy should be. So pi prime of S equals A prime such that Q pi as A prime is greater than or equal to Q pi as A for all A in A. The best possible action, any one of them, you consider that as now your new choice of action given the status. Right? So this is your new policy. So what did we need for the new policy? To do this update to the policy, what did we need? We needed our value function. This is all we need to update to a new policy. So for value function, you can always compute the Q pi as A, and once you compute Q pi as A, you can define a new policy. So this is pretty much, I think, what's. I don't want to make this thing dirty. What we have here. So this is the algorithm to say how to improve your policy. So improve your policy by acting greedily at. Oh, actually, I have a proof of it. Or what here? That is this slide containing the proof that the policy has improved?
Yes.
Okay. Good. So now this is a little bit a tricky proof. So what we have said is that we will act greedily at one step, but it could be we are talking about long-term consequences. What are we talking about? We're talking about long-term consequences. You could make one bad move in a game, which might at this moment give you a lot of points, right? But later on, it might give you less points. So how can you be sure that this has been actually an improvement? Is because we haven't actually just greedily acted at the moment. We have still used the future rewards from pi in our calculation. So this improvement was not instantaneous. This is something that one should note, that we did not just improve when we went from pi to pi prime. We didn't just say, oh, take any A which has the best solution, rather than we said, take A which has the best solution relative to acting by pi. So this has some future rewards built into this. So when you want to say that this is actually better, you know that the new policy is given by the maximum, and that when it's maximum over all of them, it's of course better than having plugged in the old action, right? It's better than having, or at least as good as having plugged the old action. So this value, Q pi S of pi prime A, is always bigger than the value of pi at S. So this is the first thing you need to observe. And then you just recursively observe that. You just recursively say that when I do this recursively, at each level, I will have a Bellman equation where I will have, every time I'll get a V pi. Here. Every time I'll get this factor, but this factor I can replace by being smaller than the Q pi, and I can recursively make it bigger and bigger. At the end of the day, when you have made all the rewards corresponding to pi prime, you keep expanding that, more and more terms will become pi prime. Every subsequent term will become pi prime. Then what will that sum be? When you have all the terms expanded and every term has become reward with pi prime, that will be the value with respect to pi prime. Or does it say something? I don't know what it says actually, but I hope it says the right thing. Well, do you see the logic, at least? I mean, if something confuses you, you should ask now, because these are the important concepts. Later on, we'll take these concepts for granted. These are very easy All right. So that was that. So we have now a better policy. Is this good enough? We'll always get a better policy. We'll always get at least as good a policy. We don't say it's better. We at least as good a policy. Then does this mean we are done? Can we ever say that we will find the optimal solution this way?
I think that we still don't know, because it might be some infinite process of improving.
I mean, the choice is good, not bad. Most likely, we stuck in some local optimal.
We could be stuck in some local optimal.
We improve upon time, but time isn't really that good for the stuff.
Okay, so in general, this can happen, but one of our assumptions is that our state space and action space can be as big as you want, but is finite. Can have millions of state space. Now, does that help? I think this also works for the infinite, but we're not going to see a proof for the infinite case. It's a little bit more thought involved, but maybe we can have this as something that we can talk about later on. But let's just look at the finite situation. So for the finite situation, we already know something. We know that the optimal there is an optimality condition. When is a policy optimal? When it satisfies this equation, the Bellman optimality equation. And when you say this has stopped, when you say pi prime equals pi, so this was pi prime before, and I say if pi prime equals to pi, I can write here pi and pi there as well. When it has stopped, v of pi prime, but pi prime is equal to pi. This should be equal to that. Okay? And this exact equation is what? This is the equation that guarantees, that we saw last time, guarantees the optimality of a policy. This is the Bellman optimality equation. So, are you guys familiar? Do you still remember this equation? You've forgotten that. So we had to define what it means to be optimal, right? Do you remember how we defined the optimality? So let me give you a quick reminder of some of these things. Maybe I should have reminded you before showing you the slide. It would be less difficult. All right, so what we said is that we can define an optimal value function. The optimal value function v star of s is max over pi v pi s. Right. So kind of brute force optimization, brute force maximal valuation says for every s, I take whatever the best possible policy can give me. I will say that is the optimal value that I can get. I don't care, but that can happen that for what you think logically, that it could be that for state 1, the maximum happens for pi 1, and for state 2, the maximum corresponds to pi 2, and so on. So can this function might never be the value function of any policy. That can happen, but what we showed last time is that actually this is why we know that there exists an optimal policy, because there exists a policy pi such that v pi equals v star. And any such policy is what we call an optimal policy, because of course it cannot get any better than that, can it? Because we are saying we are taking the maximal over all policies. So any such policy we call the maximal policy or optimal policy. Okay. And then we also said that this object, this function v star, it satisfies the equation that v star of s equals max a in a the q star s a, something like that. So we also said it will satisfy the best possible. If I act at first step very good and then do this, I will always get that. So we showed this is the Bellman optimality relation. And what do we get when we do our iteration? So now coming back to our problem. So this was a review from last time. And let's come back to the current stage. So actually, up to this point, we haven't needed much mathematics. We just have needed common sense, right? Only in the next class we'll start needing some mathematics. Because even contraction mapping theorem is some sort of common sense. If you move everything closer and closer, there is something that's not going to move anywhere. That is more or less a common sense statement. So far we have not actually used any mathematics in this course. We are already towards 2 lectures down. What time? So I think, so now we did the following thing. So this was just a reminder. And now we said that I have a policy pi, okay? And I can make from the policy pi the operator t pi, and I can compute v pi, okay? Now once I have computed v pi, from v pi, act greedily and find a new policy pi prime. How do we find pi prime? So pi prime of s is max over a belong to a, q pi s a. So that a that is the maximum of, right? Okay, so this is how you define the max of this. But now suppose you're doing this, so we have said that pi prime is greater than or equal to pi, always. That's what we prove. So we prove. So if you do this greedily, you get something better. But I haven't said it's always going to be bigger. It can be bigger or equal. So suppose pi prime equals pi. If pi prime equals pi, I can write pi here. Then I get value of, sorry, this should be v. V of pi at s equals max a belong to a, q pi s a. As soon as I say that pi prime is equal to pi, I can substitute this thing here, and what do I say about pi? It now satisfies the optimality equation that we learned last time. So as soon as we stopped improving, what do we get? The optimal solution. So if we stop improving, we get the optimal solution. Good? Everybody happy so far? All right. So I think this is what this slide says. It says that if you stop improving, you get the optimal solution. But since we have finitely many states and finitely many actions, how many policies we have? We have finitely many policies. And especially since one more thing to remember is that even if you had started with a non-deterministic policy, the first time you do the greedy algorithm here, you pick pi prime as the greedy object. The one that gets you the most value after doing the first step. That pi prime is automatically a deterministic policy. So we determine what to do in each state directly, even if we started with non-deterministic policy. So the thing is, we have finitely many policies. Can this improvement happen forever? Right? It will have to stop in finite steps. After all, you cannot go forever. So this situation will be reached. And whenever this situation will be reached, we have outputted the optimal solution. So now, with this method, we have actually done two things. There were two stages involved. The first stage was evaluating the V prime, which is the evaluation state, or what's called policy evaluation stage. And second state is using this evaluation to improve, to get a better pi prime. This is called the control process, when you're trying to improve something. Okay? So we have achieved both of them, and we have essentially gotten the optimal solution. Okay, so theoretically, if we know everything about our MDP, that is, we know the rewards and we know the transition probabilities. So if you know these two things, in general, if I'm driving a car, I cannot pre-program what R is and what P is. Right? This is something that has to be learned from experience. So even if you're playing a game of chess, video game, whatever, what do you know? What is the probability of getting the next state? You don't. So in real world problems, these two things are actually unknowns. But we have assumed that if we assume we know these two things, then at least we have one way to find the optimal solutions. Okay. Any questions so far? All right. So judging from all of this process, can you think of some way of actually bypassing some of the calculations, possibly making this process a little bit better? So this was logically done, right? We try to start with some policy and then improve it, and whenever this stops, we have the optimal policy. Now that you know this will happen, can you think of a way to bypass this? Okay, so my hint is, I have somewhere the equation. What is the equation? Not on this one? I don't know. Here it is. So you can write this in a different way as well. But I will leave it like that for now. We can write this slightly differently, which we did last time, I think. V star as is max, because I will just expand what this is. A belong to A, RA plus gamma P, V star X. So this is just expanding what Q is. So I expanded what Q is in this thing, and I get a new equation. Now, if I say that, can you think something? What does that make you feel? You can define a new operator, right? The new operator should be all of this. So you can define T star of V equals max A belong to A, RA plus gamma P V. For every V, not just for V star, you can define this. You will usually not get same thing as V when you apply this operator. When you apply T star, you usually would get something different from the V you started with. When will you get V? V is the only fixed point of T star. Okay, so this is I actually had. So I think this is basically me reminding you of what the optimal value function is, just so you know, but we have already talked about it. And then what we can do is we define a new operator, which is the maximum of this thing. But remember, this new operator is no longer an affine operator. It is a non-linear operator. It is a little bit computationally more effort. Okay. And again, the proof is exactly the same. If you copy paste the previous proof where you had T pi, and instead of T pi write T star, in exactly the same thing, with a little bit of small change, you will see that T star is a gamma contraction. It is exactly the same argument, essentially. Okay, so if you want, you can do it yourself. I would recommend it once if you're not familiar with this, to show that this is a contraction. And then again, we have contraction mapping theorem. The contraction mapping theorem guarantees that we have a fixed point, and that fixed point must be what? It has to be the optimal value function. Yeah.
Is it possible in some instances that we don't have the transition probability we just use the expectation of action? Is it possible?
Often, more or less, any real world problem, you would not have it. So this is why, so what we did last time and what we did today, it applies to very small scale problems and very few problems where you can actually compute these things, right? So from the next time onwards, we will, but all these concepts that we have done and have gotten an intuition for what a value function is, what's an optimal value function is, and so on. These concepts are what we learn in this ideal situation. And then later on, when we don't have these probability matrices, we'll figure out how to find algorithms to still solve and get as good a solution as we can. Okay, so that is to come. But let's just get familiar with the terms and technology. So this is also mathematically simple, and also it gives you a common sense perspective of what's happening. So if you were in the ideal world where everything was given to you, you could look in this way, and it is all that easy, at least conceptually. Of course, when I'm writing these equations, and suppose I have 1 million states and I have 1 million actions possible, then at some point in time I'm going to ask how much computation do I need to do that? What is the computational complexity of these things? It's pretty bad, actually. Even if you have transitional probability, if your states are large, actions are lot too many, you will see that you take a lot of effort to do this computations. Okay, but as such, they give you a good idea of what's happening. So we now have these new operator, and now we can just iterate on the value space, which is. But the point is that not every element in the value space is a value of a policy, right? So when I apply T star to V0, I can get V1, and V1 need not be value of any policy. It need not be value of any policy. It might be, but it need not be, but I don't care. I keep applying T star till it converges to something. And when I have something convergent, then I can pick the final value as to be my optimal value function for my MDP. And from the optimal value function, one can always construct an optimal policy. This is what we just reviewed as well from lecture 1. So from optimal value function, you can all. But in between, when you keep applying, so you start with an arbitrary first value function element of the value space, and keep applying T star repeatedly till you converge. In between, you don't get functions that are value functions for any policy. Okay, is that good? So I think because I'm going to more or less stop this lecture today at here, because it is not going to be easy to start the new concepts, but I will give a little bit about implementation of these policies, and then a little bit of overview of what is to come. Okay, so the implementation of these policies, actually, I didn't write the algorithm clearly down, right? So let me first do that for a second. So what is our second algorithm? So we have one algorithm that we already saw, and we have a second algorithm, and I don't want you to confuse between the two. Okay, so we actually are going to look at two algorithms today. In the ideal case scenario, the planning case where we know everything about our MDP. So the first thing was for finding optimal policy for MDP. That is our challenge, and this is the case when we have all the data for the MDP. So we know what the reward and what the transition probabilities are. We know these two things. Okay, so this is usually not given to you in practical problem. This is what we'll see next time. Okay, but now we are looking in this case, and we saw the first thing that we saw was the following. So start with pi arbitrary, evaluate v pi by finding the fixed point of t pi. And how do we find fixed point of t pi? So we start with v naught, anything in v, and you say v1 equals t pi v naught. v2 is again applied, t pi v1, v3 is t pi v2, and so on. Keep applying that. So you get the sequence v0, v1, v2, vn, and we say v pi will be the limit of vn. So basically, how do you do this in practice? How can you say I have found v pi in practice? Any guesses? Any suggestions?
If Vn is equal to Vn plus 1.
That may not happen, I think. So you usually would need to fix some error which is immaterial to you. So pick some small number epsilon greater than 0, and when the norm of Vn plus 1 is less than epsilon, that's when in practice you will say, okay, this is now good enough. Right? This is now good enough. I'll converge this as my, consider this as my solution. But of course, you can solve this other ways. I don't mind. But let's just consider this. This need not actually, even in finite dimensional cases, you need not. But this has a convergence rate of gamma. So after n step, you have gamma to n of something involved, and this is very fast. Okay. So we'll talk about this maybe next time, sometime. So this is our first step. Find this. So I'm going to recall this again, just to make the difference very clear. And then once we have v pi, we can define pi prime of S to be the A for which Q pi S A is greater than or equal to Q pi S A prime for all of them. The best possible action with respect to Q pi, well, Q pi we know how to write Q pi. So this is how you improve your policy, okay? And then you say, we keep repeating this process till pi prime equals pi. So when that happens, this will happen in finite step, and this will be an equality, so to speak. Oh, when I said this, by that I mean v pi prime equals v pi. Then we output. So this is our first algorithm, right? We checked all the essentially important things, why this algorithm converges to the optimal pi. So this, we have checked that this will be an optimal solution. So this is how optimal policy. All right. So this is one algorithm, and it has a name. Its name is policy iteration. Good. Now let's look at the second algorithm, which was much shorter, and it's called value iteration. And for value iteration, we don't care about having any policy at all. You start with any v naught in our space V, which is all maps from S to R. So start with arbitrary V naught. Okay, and then V1 is T star of B naught, which is max over A belong to A, R A is gamma B naught. Okay, and similarly now V2 will be T star V1, and so on. Vn will be T star Vn minus 1. All right, and I will say that we get V star equals limit Why is this true? It's because T star is a gamma contraction. And P star V star equals V star. So V star is a fixed point and you have a contraction. So whenever you apply this recursively, you will end up finding the fixed point. Okay. So once you have V star, you can define from V star the optimal policy by first defining Q star as A because max over A belong to A R A plus gamma E V star. Okay, so finding finding the maximum of all the things that you can do defines a policy that we did how the maximal policy exists. So whenever you get the V star, you automatically can define Q star, and from Q star you can define Q star defines the optimal policy. So phi of S equals A such that Q star as A is bigger than equal to Q star as A pi. So this is how you define the optimal policy given Q star. So in this process, we don't think about the policy anywhere. All these V's need not be, they need not be equal to V bar. Okay, they can be just some functions. We don't care what they are. They are not related to any policy. But you can compute them, and when they converge, you can construct out of the value a policy. So this is the value iteration algorithm, and this is the policy iteration algorithm. And both have their advantages and disadvantages. Okay? So is the difference between these two things clear? Or let's just pause for a minute and think. And once you have thought, you should tell me what are your concerns, if you have any. So I've revised the whole lecture here once, and you can tell me if you have concerns about what we did so far.
Can you move on to the other board again?
Sure. So I can only keep one really visible. I will move it down when other people want. Any questions?
I have a question.
Yeah.
I wasn't present in the previous lecture, so this is my first, so maybe you've discussed this there. But how are we sure that V star is a function that corresponds to a policy that exists, the optimal V star?
Yeah, so this is kind of the logic I have tried to quickly summarize here. We did it last time. I would put some sort of information from the first lecture online soon. So because I think many people thought it will be streamed, but unfortunately it couldn't be. So the argument is precisely that when you have a V star, the optimal value function you define, you can use it by a straightforward formula to define this function Q star as A. For every action, you take the action, get the reward of doing that action, and then added the V star, right? So this is a Q star function, and this Q star gives us a way to define an optimal policy. So the policy is defined by, at any state S, take the action that gives you the biggest value of Q star SA. So this defines a policy, and since this policy will have its V star will be equal for this policy, phi B equals V star. This is what we checked last time. Since for this policy we get the value of this policy is that, therefore we know that this policy has to be the optimal policy.
Thank you very much.
Yeah.
That's very clear.
So this process actually brings you around, and so this is basically a very theoretical kind of argument, but it's good to have conceptual clarity as why we can do these things, because later on when we do other things, we will assume that all of this works, right? Okay. That was a good point. I should have mentioned that here. Yeah. Anything else? So, by the way, for those who were not here, I don't see well. Yeah, don't just raise your hands. You're welcome to raise your hands, but you should just speak, because I might not detect your hands. Probably I won't. Most likely I won't. So that's also a stochastic process, by the way, whether your hand will get detected. Okay, so I'll quickly mention some things about the implementation of these algorithms, and so especially the value iteration process, I think, which is the board behind, where you keep T star, applying T star to get the thing is, how do you update these value functions? How do you update the value function? What you can do is, one obvious thing which we can obviously prove from our thing is what's called the synchronous update, where in each step you update all of your states. You update all of your states before you go to the next value of n. Right? So you use the previous n-1 state's value all the time, right? But this is an expensive algorithm. So I have put a comment there. You should tell me what the complexity is. Maybe this is a homework for next time. So I need to know. I will ask you again. What is the complexity of actually doing it this way? We'll talk about complexities sooner or later, but I think most of you are familiar with. How many of you are familiar with complexity of an algorithm? Computational complexity. Can anyone tell me a percentage? Not many, right? My guess. 5%. Okay, then that was the wrong question. I somehow believe that people know what that means. Okay. Then it was good to ask this question, to do this survey. Anyway, so this is a very computationally expensive process. Let's just put it like that. You need to do a lot of computation to do it. So if you fix a number of states to be n, a number of actions to be m, you get something like m times n squared or something like that. Number of computations in each iteration. The sort of cubic number of computations, which is a lot to do. Okay, so other ways are then most other value iteration algorithms that you will see will not go through this like that, but they will make sure that each state is repeated often enough, right? And those are called asynchronous algorithms, and they also converge for precisely the same logic as we saw this basic algorithm to converge. There is no mathematical difficulty in these things. So there's just about a comment about implementation. So yeah, so that will be essentially all for today. I'm going to quickly tell you something about what we'll do tomorrow, next week. And also that now we have covered the basics. Before next week, I will put up information on what you could do as papers or projects. Okay, so I think I'm going to, well, anyways, I'll keep this thing running for a bit. Where is the? So the only thing now, so theoretically, if you just care about the theoretical aspects, if you believe that all of your data can be given to you, if you can believe that this is given to you, you're done, you can go home and sleep. Right? But the whole problem and whole interesting thing actually starts from here. Okay? So when we are not given this. So this is what we'll start next time. And it's not that difficult. It requires you to at least know things like law of large numbers, but not too complicated stuff. So this is the first thing. Second thing is there is something about these algorithms that I've just showed. Both this algorithm 1 and the algorithm 2, they're both examples of what's called dynamical programming. So when a mathematician says the word programming, what does that mean? Does it mean a C program, a Python program? Huh? No. It just means optimization. So linear programming means optimizing a linear function with linear constraints. Okay. And dynamic programming means optimizing a function which is a time-dependent function. Okay. So here we have some time-related thing, and if you are trying to optimize it, it's dynamic programming. That's the language, so to speak. That's what we are doing. We're trying to optimize a problem. So we are doing dynamical programming, so to speak. And a key part of dynamical programming is having a recursion somewhere. Right? So what we have, we said that p pi of v pi equals v pi. This is a recursive relation. In some ways, you could keep applying the same operator till you converge to the fixed point. So you need some sort of a recursion to apply such algorithms. Okay, so there is a whole set of mathematics where you need this structure of recursion and something that you can update, like the v pi, which you can update sequentially one after the other. Any such problem structure is called a dynamic programming problem structure. So the basic theoretical solution for the decision-making process is the good old dynamical programming thing, which unfortunately requires you to know these two things. Okay. From next time on, we'll see what happens when we don't know these two things. All right. So that's all for today.
Thank you.